In today's session, I'm going to teach you on hypothesis testing. Hypothesis testing is one of the important topics that you need to understand in statistics. So, what is an hypothesis? Hypothesis is nothing but a belief, an assumption that is made. So, what is hypothesis testing? So, whatever assumption that is made by a person or someone, if it is true or not, we have to test that assumption. So, in hypothesis testing, we have two types of hypothesis, that is null hypothesis and alternative hypothesis. So, we will look into these two types of hypothesis in the later video, in the video that I'm going to discuss on hypothesis. So let me take an example of hypothesis. So let's say an average salary of a data scientist around the world has changed post COVID-19. Let's say this is an hypothesis, okay? This is not a fact. This is just an hypothesis that is made by some individual. So let's say the average data's current average data science salary is $1,000. Okay. So now let's take a case one where X bar is average salary of a sample. So this is average salary of a population. So now we have considered average salary of a sample, and it comes out to be $90,000. Can we say if the average salary has changed? So if you see 90,000 is so close to $100,000. So we can't say this deviation might be due to random variability also. So difference is not significant. Difference is almost close to 1,000, 100,000. So we can't say that the whatever assumption is made by someone is true or not. So let's say case two. Okay. So average salary. So sample mean is $110,000. So can we say if the average salary has changed? So here also this deviation might be due to some random variability. Okay? So here also difference is not so significant. So we can't say if the the average salary of a data scientist has changed or not. So now let's consider the third case where a sample mean is $125,000. If you see, our mean is 100,000 and our sample mean comes out to be $125,000. In this case, we can say the difference is significant. Okay, there is some particular point till that point you can say if the difference is significant or not. If you consider the last two cases, case one and case two, the average salary of the sample is close to the mean value, that is $100,000. So we can't say that difference is significant. But in case three, you can easily say that there is a significant difference between $100,000 and $125,000. Okay, so you can say what is this is difference is significant. So till what point would you able to say that this hypothesis, whatever is made, is true or not? Okay, so let's say this is our curve that we have drawn. So here is our acceptance region. This is the normal distribution where this is our average acceptance region and this is our rejection region. So when you have made that um, statement that average salary of data scientists around what has changed, you can say from mean we will have some kind of confidence interval. Confidence interval in the sense till what value we can be sure that that value is like alternate hypothesis is acceptable. I mean, let's not think about alternate hypothesis for now. Let's understand. If you say the average salary of a data scientist exchange till you can say till from 80 till $120,000, it is acceptable that it is not changed. Okay, acceptance region, that is that data scientist salary hasn't changed, we can accept it since difference won't be that much significant from 80 till 120 because the significant difference can be due to some other factors as well. When you consider if the average salary of a data scientist sample that we have taken crosses the 120,000 or crosses the less than 80,000 region, then we can say that point point estimate, okay, after when it crosses this point, then we can say that lies in the rejection region and we can easily say the difference is significant. So you have to understand that from mean till what point where the acceptance region comes, that is to the left or to the right of the mean, and that is called as acceptance region. Okay, or it is also known as tolerance region, or it can be called as confidence interval. Confidence interval tells us that till what percent of value we are going to accept the statement that is made, that is the hypothesis. Okay, so since our value lies, then case 1 and case 2, we can easily say the value lies between 80 and 120K, and that difference is not so negotiable. So we can't say that whatever hypothesis has been made, that is not true, because average salary of data is certain, although the world has changed. It can be not true. That comes under null or alternate hypothesis. I will teach you on that. So let's come. So rejection region is the region where the null hypothesis is hold false. That hypothesis, whatever is made here, this is going to be true in our case that average salary of data scientist has changed. In the case 3 only. In case 3, that case 3 assumption will be true because our mean sample comes out to be 125,000, which is much difference is significant. Let's come to point estimate and confidence interval. So let's say point estimate is its particular value. If you are saying, let's say I will tell you that I'm going to take a class tomorrow. So I'm giving you that particular value on what time I'm going to take. That is the point estimate. But if I'm going to say you that I'm going to take a class between 7:45 to 8:15 p.m., then it's like a confidence interval, right? I mean, I'm going to take the class between 7:45 to 8:15, but I'm not going to cross this limit. Like I won't be taking a class at 7:44 or 8:15, but I'm giving that confidence interval that within this range, I'm going to do this. This is the confidence interval that I want to discuss. Now let's come to the technical discussion. As I said, in hypothesis, there are two types, null and alternate hypothesis. And null, let's say a null hypothesis assumption has been made that Earth is not. So whenever there is a problem that you get, you have to understand that whatever statement has been made in that problem statement, it is always alternate hypothesis, okay? And you always reject or accept null hypothesis. Let's say there is a statement that Earth is not flat. Then whatever statement that is made, that is an alternate hypothesis. Then what will null hypothesis will become? Then Earth is flat, okay? So let's see the case one. So we always try to accept or reject null hypothesis only, okay? In case one, we will reject null hypothesis. In case two, we will be able to fail to reject null hypothesis. Here, two cases that will be possible. So let's see what is acceptance tolerance region. Okay. So how to construct acceptance region or tolerance region. Okay. So this is the acceptance region or tolerance region. So we have to construct this in our from our data points. So let's see how we can consider. So now this is the we can say mu plus or minus gap. Gap is this part, okay? Mu plus gap or minus gap depends. The gap is the Z score into standard deviation error, okay? The Z score into standard deviation error gives the acceptance region or reject the tolerance region, okay? So this is the gap, okay? The from right hand side and left hand side. Let's say, so if you see at what probability I want to construct my confidence interval, this will give. And whether it is one tail test or two tail test, you have to decide from the problem statement. So in this, let's say we have a confidence interval of 5 to 95%. So when you have a confidence interval of 95%, then the significance level becomes 1 minus confidence interval. That is 100% minus confidence interval. That is 100 minus 95. That is 5%. So if a region, if whatever your problem statement is considered, if it is a tool tail test, then 5% significance level, whatever you have, it will get divided by 2, so that in the right hand side of the mean, we will have 2.5%, and in left hand side of the mean also, we will have 2.5%. Okay. So how to decide Z value in hypothesis? Okay. So I already told you. So this is when you have. I wanted to show you on T table. T table. T table for negative and positive values. Okay. Let me check. Okay. Let's view this image. So whatever value you have in the x-axis over here, this is mu. Okay, this is the mean, and mean plus or minus. This is standard deviation. This is kind of a normal distribution curve, if you see. And this x-axis, whatever you can see, that is the z-score. So this is the probability distribution. How much data, how much our data points is distributed across the region. So if you see across mean from left hand side and right hand side, we have equal distribution of data points. So now let's say we have 2.5% of the data points over here falls in the rejection region. So then we have to go to T table. Uh, So this is not a T table that we had to say. We have to consider Z table. Sorry, okay. Let's go to Z score table. Z table, we'll see that Z table if it is present. Okay. So we have got one Z table. Let's take that Z table into consideration. So this is the Z table we have. So we have the probability percent to be 2.5% in the right hand side. So if you see here is the 2.5%, right? Let's take the left hand side 2.5%. From here, from infinity to value minus 1.96 as Z score. That I'm going to show you. But 2.5, let's see what is the percentage probability of 2.5%. What is the Z score? So from the hypothesis, from the Z table, if you go here for the distribution, see this is a distribution of 0.5% rejection region on the left hand side, and here also we will have a 0.5% rejection region on the right hand side for a two-tailed test. Okay. So for this, since our consideration is a two-tailed test, for 5% of significance level, we will have 2.5% of rejection region in left-hand side of from the mean and also in the right-hand side of the mean. So let's see what is 2.5%. Like what is the z-score for 2.5%? That is 2.5% means its value could be 0.025. Okay. So just check what is the value of 0.025. If you see minus 1.9, 0.027, 0.026, okay. The value of that score comes to be 0.025 for the value of z score for 0.025 is minus 1.96. You have to read it like this, okay? This is minus 1.9 and this is 0.6. So minus 1.96, okay? So the value of my negative value goes to be minus 1.96. Similarly, it's like a mirror image. So here it's 2.5%, right? It will comes out to be plus 1.96. Let me show you. So what is this region? This dejection region is 2.5%, right? So from here till here, we will have 97.5% of the values, okay? So let's see what is the 90.975. Okay, we have to consider from here till here, it's 97.5, right? So it comes out to be 0.975. Okay, 0.975. Let me check what is. So here, if it is mine 0.9750, that is my 1.96. Okay, this value comes out to be 1.96. So for whatever p value you got, this is the p value. You have to understand that this is the p value. This is p value. This is z value. This is probability value. Okay, the probability value whichever you are checking, that is here you are checking probability value of 2.5, and for him here, and here also from 2.5 from the left hand side, the right hand side. So 100 minus 2.5 comes out to be 97.5. So this is 1.96, and we have got it from the Z table. Okay. Now, how to decide Z value in hypothesis testing? So if you want to decide Z value in hypothesis testing, so what is the value that comes out to be? It depends on the confidence interval. Okay, you either need to know the confidence interval or you need to know the significance level. Confidence interval always is the acceptance region. Okay, this is the acceptance region for a total test here we have shown. It always gives the acceptance region, and significance level always gives the rejection region. For a two-tailed test, significance level, whatever is mentioned, it goes by half. Okay, if I have 5%, then it will divide into 2.5 into 2.5. If it is only one tail test, that is right tail test, then it will give 5% here. So confidence interval and significance level helps us to decide whether Z value in hypotesting. So acceptance region plus rejection region will become 1 or 100%. Confidence interval plus significance level becomes 1 or 100%, or confidence interval plus alpha, that is significance level is represented by alpha, is always equal to 1. Okay. So let's take an example where we have a alpha equal to 5% and we have a two-tailed test. Okay. When alpha is equal to 5%, then confidence interval is 95%. So from here to here, it will be 95%. So alpha is 5%. So rejection region for a two-tailed test will be 2.5% over here, 2.5% over here. So for p value of 0.025, the z score becomes 0.025, 0.025. 0.025 z score becomes, you take here minus 1.9 and you take here 0.06 minus 1.96. Okay. So minus 1.96 here. So similarly, 1.96 will come over here. It's like a mirror image, you just think. Okay. Then from negative, since mean is zero, mean is zero here. So it will be a mirror image. So here, whatever value you get, you will get the positive value over here. So one tailed or two tailed test. Let's say case 1, where your null hypothesis is mentioned as mu is $100,000. Then what will it be the alternate hypothesis? If your mean is $100,000, then alternative hypothesis will become either it is less than $100,000 or it is greater than $100,000. But one thing is, it cannot be $100,000 because null hypothesis says it is $100,000. So less than $100,000. If this is 100,000 less than 100,000 shade that region, and greater than 100,000 shade that region. So we have that shaded region as a rejection region. Now we have to reject null hypothesis. This is a two-tailed test. This is for alpha equal to 5%. When alpha is equal to 5%, as I said, it will get divided into 2.5 and 2.5%. Let's say the case 2 where null hypothesis states that mean is less than 100 or equal to $100,000. Then when it is said mean is less than or equal to $100,000, then obvious that the alternate hypothesis becomes mean greater than $100,000. When it is mean 100 greater than $100,000, this should be rejection region, because less than or equal to is null hypothesis and the rejection is greater than 100,000. Here also we have to reject or accept alternative hypothesis. We will look in the later section that I'm going to teach. So this, whatever alpha value given, this is 5% because this is only a right tail test. Okay, one tail test. This was two tail test because it was less than or greater than, but it is only greater than for hypotenuse. So alternate hypothesis. So we have one tail test, which is the right tail test. And you want to find out right now what is the value of this 5%. So if this is 5%, this region is 95%. What is the value for a 95%? So from here till minus infinity till here, 0.05, we have to find out the Z score. So Z score 0.05, you find out 0.05. That means it's 0.95, okay, because this is 0.05, right? 5%. But from here till here, we have 90% of the data points is there. So probability value of 0.95. 0.95 where it is 0.95 comes out to be here. If you see 0.95, 0.9495. If you see that value lies between minus 6, 1 with that 1.64 and 1.65. Let's take it as a 1.65. Okay. So we have taken our Z score to be 1.65. And let's say that case 3 where our null hypothesis states null hypothesis is greater than or equal to 100K. So alternate hypothesis less than 100K. So null hypothesis is the acceptance region is this thing. So greater than 100K, we have to reject null hypothesis. This is the rejection region we have to take. So since our alpha is 5%, here also for our 5% alpha we got 1.65. For alpha 5%, you'll get minus 1.65. Let's check from the Z table. So what is the value? Now we have 5% only, that is 0.05, 0.054, 0.05, 0.05 comes out around here, 0.0505, 0.04905. So comes out to be minus 1.65. Okay, so this is one tail test and this is left tail test, whereas this is the right tail test. Okay. So now let's see an example for hypothesis testing. So a researcher has agreed upon a data on a daily portfolio of call option over a recent 250 days period. The mean daily return has been 0.1% and the standard deviation of daily return of portfolio is 0.25%. The research believe that the mean daily portfolio return is not zero. Construct a hypothesis of researcher claim at 95 days confidence, 95% confidence interval. What is the alternate C? Whenever there is a question and they are mentioning about that hypothesis, it is alternative hypothesis. Okay. So the researchers claim that mean daily portfolio is return is not zero. That is alternative. So what is the null hypothesis? It is zero. Okay. So null hypothesis becomes zero. Mean is zero. Mean daily portfolio return is zero, and alternate hypothesis is not zero. That is the step one. Define hypothesis. H naught and H. So now step two, choose type of test. Z test, tails of test. So if you see from here, I have alternate hypothesis says mu is not zero. It can be less than or greater than zero, which is a two-tail test. Okay, mean can be less than zero or greater than zero. That is here also rejection region, here also rejection region. That is a two-tail test. So we have our two-tail test. Now let's construct our acceptance or rejection region. So now we have given they have given that the confidence interval is 95%. So what is the significance level? 1 minus 0.95, which is 0.05, that is 5%. Okay. Significance level alpha is 5%. That the acceptance region is mu plus or minus Z score into standard deviation error. Okay. So now whatever Z mu is there, this is our H naught. That is null hypothesis mu. Mu is zero. Plus Z score, whatever Z score we have got for a two tails test with alpha is equal to 5%, we get Z score to be 2.5 in both sides, 2.5%. Let's see on the negative side. For 0.025, the value comes out to be minus 0.025, that is minus point zero, that is point sorry 0.025, the value comes out to be minus 1.96. Okay, minus 1.96, minus 1.96. So our value of Z score is 1.96 or plus or minus 1.96. Okay, let's give plus or minus because it's plus or minus 1.96 or minus 1.96 since it's a two-tailed test. Okay. The standard deviation error is sigma by root n. Okay, sigma by root n. So what is the sigma that they have given? Sigma standard deviation of daily return is 0.25%. That is 0.0025 is the standard deviation. And what is the total recent 250 days period? So now number of days is 250. So 0 plus or minus 1.96 into 0.0025 by 250. When you calculate this, the acceptance regions comes between minus 0.0003 and plus 0.003. That is our mean. The mean should lie between this region. Okay. So what is our really mainly mean daily return that has been 0.1%, which is 0.001. Okay, 0.1% is mean is 0.001, but our mean actually should be lying in this region, lower between lower and upper limit, since 0.001 is outside this 0.003 and minus 0.003 and plus 0.003. So we can say that, so we'll check if we can say that since x for x bar, that is this mean daily return, falls outside of acceptance region, hence null hypothesis is rejected. Okay, we have rejected our null hypothesis, and hence research claim is correct. Okay, research claim of that mean daily portfolio return is not zero, that is correct. Okay, and null hypothesis is incorrect. Research claim is correct. You have to understand the step for whatever you have shown here decision. We'll check if my x bar lies between lower and upper limit. So x bar is this thing, 0.1%. And if it has failed to reject null hypothesis, if no, it doesn't lie, we have to reject null hypothesis. That is what we have made. So points to ponder in hypothesis testing, like we have seen hypothesis and hypothesis testing, and we have seen null and alternative hypothesis and how to frame that. And we have seen acceptance region or tolerance region and as well as rejection region. We have seen how to reverse lookup to Z table based on the p-value that we get. We have seen tails can be one-tailed or two-tailed test. We have also seen confidence interval and point of estimate. And also, whatever area, what for this reverse data lookup table which are mentioned, the area is the probability area, that is the distribution area, whatever distribute, how the data points are distributed based on that, the Z value can be calculated. Now, then we have seen the significance level, alpha. Then we have done hypothesis testing using acceptance region, tolerance region, and rejection region. Let's do hypothesis. Let's apply hypothesis testing method for p-value and critical value method. Let's see a second example now. So, a principal at a school claims that students in his class are above average in terms of intelligence. So, what is the principal claim? Above average in terms of intelligence. A random sample of 30 students' IQ score was found out, which has a mean of 112.5. The mean population IQ is 100 with standard deviation of 15. Test the hypothesis of principal's claim. Let's see. So, what is the hypothesis they are saying? The principal claim is students in his class has are above average in terms of intelligence. So, what is the mean population IQ? That is 100. Okay, and what is the principal claim? It is above average. So alternate hypothesis is above 100, right? So alternate hypothesis is mean value is above 100. So when alternate hypothesis is above 100, what will be the null hypothesis? That is less than or equal to 100, right? So we have greater than 100 is our assumption, and alternate hypothesis and null hypothesis becomes less than or equal to 100. Now, since we know that for alternate null hypothesis, acceptance region becomes less than or equal to 100. This is the acceptance region, okay? So whatever value greater than that will be our rejection region. This is a 2-1 tail test, which is right tailed, okay? As I see here, mu greater than 100k, mu less than or equal to this, from less than or equal to will be acceptance region, and this is a rejection region. So if value lies here, then alternate null hypothesis get rejected. Okay, we have to always consider the null hypothesis. Just remember, so less than 100 is this acceptance region, and greater than that is rejection. So now we have alpha as 5%. So for alpha as 5%, since it's only a one-tailed test, we have to check where the 0.005 lies. From here till here, we will have 95%. We have to check that value. Okay, since 5% is for the right-hand side, for the left-hand side, it comes out to be 95%. Z alpha of 95 comes out to be 0.95. So 0.95 is here, okay, in 1.65. 1.565 grams. This Z score is 1.65. So now let's do the Z calculated. So this is the method one, that is critical value method or z-score method. Okay, this is another way how this is the another way to tell if your assumption, that is your hypothesis, null hypothesis, is true, or we have to reject that null hypothesis. So we can calculate that z calculated value, and you have to understand that one thing, that if z alpha, the z alpha is less than z calculated, then you have to accept null hypothesis. If z alpha is less than z calculated, then you have to reject. That is, if z calculated is less than z alpha, then you have to accept null hypothesis. If z calculated is greater than z alpha, you have to reject. Because just think technically, okay? Your Z value over here 1.65, and your Z calculated, this is the Z alpha, and your Z calculated comes out to be around 2.1. So where the Z calculated rise here, right? So this is the rejection region, right? So based on that value, you can say if Z calculated should be less than Z alpha. I mean, it should be like less than 1.65. If it is greater than 1.65, then we can say they have to reject null hypothesis, because the Z calculated falls in rejection region. Okay. So let's see what is the value. So we have our X bar. X bar comes out to be 112.5, because we are taking X bar, right? Mu is 100, but the random sample 30 students values we are taking. The sample of 30 students IQ is 112.5. So X bar is 112.5 minus mu is 100, mean of this is the mean population. This is the sample population of 30 students. So mean population is 100, mu is 100, X bar is, that is sample mean is 112.5 minus 100 divided by sigma by root n. Sigma is what? Standard deviation, and that is for what? Mean population. Then what we have to do for 30 students, divide by root 30. Okay, so 15 by root 30. Okay, so we got Z calculated from 4.56. So if you see Z calculated, we got as 4.56, which where does it lie? Z score 4.56. It will lie in the right hand side, right? So we know that Z calculated is greater than Z alpha. So what we can say, we have to reject alter the null hypothesis. Why? Because it lies in the rejection region. So principal claims is correct, that what was the principal claim? That the school claimed that above average in terms of intelligence. Students' IQ is above average. That is claim is true. Okay. So let's see another method. This is the principal p-value method. So how we can calculate using p-value method? So how we can calculate is, so you have seen, right, the alpha whatever we got is 5%, right? So that is the probability value. So 0.005, 0.5 is our value. And p-value for calculated. So whatever z value you got, z calculated, for that z calculated, you have to find out in the Z table what is the P value. So if you see, this is 3.4 till 3.49 we have values. Let's take 3.49, right? Let's say 0.99998, okay? 4.5 we don't have value because very less data points present there. Very less means less. So let's say 99.99% of the data points are there. So it will be like 100 minus 99.59%, because here we are seeing how many data points. This is from here till left hand side we got 99.9%. But right hand side, if you want to see how much data points, like I said, see from here till here it is giving 99.99%. Okay. From right hand side we want, right? So we will check what is the value 100 minus 99.99. It comes out to be 0.000001. But what is the alpha value? 0.00. So where does that 0.0001 lie? It lies here, right? Because our alpha value is here. P value should have been greater than 0.05. If our P value had been greater than 0.05, it would have been lied here. I mean, more than 5%, like 6, 7, 8, 9, 10. Then that for P value for Z calculate, if it had been lying there, then we could have said it lies in the acceptance region. But if you see the P value is 0.5% and it's less than that, that is 0.00001. So we can easily say that it lies in the rejection region. So p-value calculated is less than alpha, so it lies in the rejection region. So reject null hypothesis and accept alternate hypothesis. So we have already seen that AR acceptance region, tolerance region method. I would like you to do this on your own. So you have these values. Let me tell you what you have to do. So we have using acceptance region formula. We have this is the acceptance region. Here I wanted to say what is the mu. So substitute mu is equal to 100 for mean population. We have to take 100, and standard deviation is Z is 1.68, 1.65. Okay, Z, and here it is only one test, right? Test, right? So you have to not consider minus. It's only plus 1. Plus only since it's a right trade. And you have to take what is the next value. You have to take standard deviation is 15 and number of samples is 30. So substitute this value over here, standard deviation, the 50, substitute part, and number of this thing 30 root 30. And they you will get an upper limit. And if it is upper limit, whatever value you get, if it is actually above, if this value, whatever this value which we got, what is the value? And 112.5, right? So you can see 112.5, it whatever upper limit you will get, it will you will get almost 104, and 104 is this point. Let's consider here, and we get our 112.5 is the mean of samples, so which is lies in the right hand side of that. So it lies in the rejection region. You could easily say that you have to reject null hypothesis and accept alternate hypothesis. Okay. So now let's come to framing hypothesis practice. Okay. So how we will frame hypothesis. So a new teaching method is developed that is believed to be better than the current. Whatever statement will be given in the problem, you have to consider that as your alternate hypothesis. Okay. So a new teaching method is developed is believed to be better than the current method. So new teaching is greater than current method. Okay. Then if our alternate hypothesis is like that, what will be our null hypothesis? New teaching is less or equal to less or same as current method, right? Next, let's see the next problem statement. A new drug is developed with the goal of lowering BP more than the existing drug. So what is our alternative? New drug lowers BP more than the existing. Then what is our new drug? New drug is same or worse, less or equal to the existing. That is the alternate than hypothesis. Okay. Have to understand that. The next topic is about the degrees of freedom. So degrees of freedom refers to the maximum number of logically independent values in a sample. Let's say we have three, five values over here, and you can see we have been given the average. So if you want to find out the value of x, it is dependent on the average as well as all the values over here. So if you add up the values 3 plus 8, 11 plus 5, 6 plus 4, 20 plus x divided by 5 is equal to average 6. So x comes out to be 10. So if you see here, x is dependent on all this, okay? But if you see how many values are there, there are five values. But you know that four values are independent and one value, that is x, is the dependent one. Okay. So if you see here, we have five values where x and y are dependent. And if you see, the value of x is dependent on y, and the value of x can be dependent on other values as well. So here we have two dependent values, but in degrees of freedom, you have to understand that degrees of freedom refers to the maximum number of logically independent values in a sample. That is n minus 1. If we have n data points, then we have degrees of freedom is n minus 1. That is 29 are the independent values. So degrees of freedom will be 29 for that. Okay. So let's calculate there is another problem. So let's see the average weights of students of my class is 168 LBS. Average weight mean is 168. A nutritionalist believes that the true mean is different. Okay, nutritionalist hypothesis is or that one mu is not equal to 168. So what will be the null hypothesis? That is mu is 168. Okay. She measures the weights of 36 individuals, n is 36, sample size, and found to mean to be 169.5. So mean of x bar is 169.5. That is mean of the sample at standard deviation of that 3.9. Okay, standard deviation is 3.9. At 95% confidence interval is there enough evidence to discard the null hypothesis. So we have the significance level of 100 minus 95, 5%. So let's form the Z score using Z calculator. So for first, let's see null hypothesis. So we have a mu is equal to 168. So mu can be less than or greater than or 168. So we will have for 5%, we will have 2.5% distribution, 2.5%. Yes, so it's a two-tailed test. And it comes out to be 0.1 minus 1.96. We have already seen that, right? So let's see that calculated, right? So x bar minus mu by sigma by root n. So it's 69.5 minus 68 by 3.9 by root 36. And the value comes out to be 2.3. Where is the 2.3 lies? This is 1.96, right? So 2.3 lies in the rejection region, right? So Z calculated is greater than Z alpha, Z critical. So reject null hypothesis. So whatever assumption made by the neutralist is true. So you can do that using a p-value test as well. I would like you to make, I would like you to try the p-value test as well as the another acceptance region using acceptance region and check what is the value you will get. Okay. So now let's move to the next topic. So the now new topic is the errors. So there are type 1 and type 2 errors. So how we will get type 1 and type 2 error? Let's see. So let's say the actual value is true and the prediction is so these are the actual values. Let's say true and false, and your prediction is this. Okay. So let's say your prediction is false. Okay. So whatever you predicted, it is false. Let's take this example. So actual is positive and negative. Prediction is negative and positive. So actual is positive, prediction is negative. What it is? Type 1 error. That is true null hypothesis rejected. And actual is negative, when predicted is negative, this is fine. Actual is positive, predicted is positive, fine. And actual is negative, prediction is positive. This is a type 2 error, which is false hypothesis null hypothesis and you fail to reject the null hypothesis. That is type 2 error. Okay. And probability of type 1 error is also probability of type 2 error is beta. So I will give you an example for this. So let's say just understand that if uh, if there is a null hypothesis and you reject the null hypothesis, then it is a type 1 error. And if the null hypothesis has to be rejected, but you accept the null hypothesis, that is, if you fail to reject the null hypothesis, that is type 2 error. Okay. So once again, I'm repeating, if you reject null hypothesis, which is supposed to be true, then it is type 1. If you fail to reject null hypothesis, which is false, then it is type 2 error. So let's come to the concept. Let's take an example. So a man predisposed to heart disease have to have a mean cholesterol level of 300 with a standard deviation of 30. But only men and cholesterol levels of over 225 are diagnosed to heart disease. So find probability of type 2 error. So men predisposed to heart disease have mean cholesterol level of 300. So what is, let's take alternative hypothesis. The person is predisposed to heart disease. That is what is said. So null hypothesis says person is not disposed to heart disease. So what is the Z score that we want here? So Z score is x minus mu by sigma. What is x value? If mean men predisposed to disease, we have a mean cholesterol of 300. Okay, this is our mu value. And but only men with cholesterol of 225 are diagnosed to heart disease. This is as x value. So x minus mu by sigma, standard deviation of 30. So it comes out to be z score of minus 2.5. Okay. So at minus 2.5, what is the p value? Let's check. Okay, minus 2.5, right? So minus 2.5, p value comes out to be 0.0062. Okay, so 0.0062. This is the type 2 error. So find probability of type 2 error, that is 0.00621. So let's say above what cholesterol level should you diagnose the people with heart disease if you want probability of type 2 error as 1%. So they are giving probability of type 2 error as 1%. Let's see 0.001 value where it lies, 0.001, right? 0.001 where it is 0.001, right? It should be around here. 0.0099. Okay, so 0.0099 is here, 0.001. So minus 2.32 is the answer. Minus 2.3 plus or minus 2.3, since it's a two tail. Since it's a left tail test, we are taking minus 2.3. Okay, so minus 2.3 into, so you have to take z is equal to x minus mu by sigma, x minus mu, that is x we have to calculate. So what is the cholesterol level we have to calculate? In this example, we had been given the cholesterol level, but we had to find probability of type 2. But we have to find out the type, what is the cholesterol level for 1% type 2 error. So now we have x minus 300 mu by sigma 30, x minus 300 into is equal to 30 into minus 2.3, is comes out to be minus 69. So x is equal to 300 minus 69, it comes out to be 231. So if you want the probability of type 2 error to be 1%, your cholesterol should be 231. So similarly, if you want to 5%, 0.5% of probability, then you have to see what is the 0.5%. This is 0.005 value. And if you want 0.005, it comes out to be 0.005, yeah, 0.0051, right? So it comes out to be 2.58, 2.57, 2.58, okay? X minus 300 by 30, and it comes out to be 222.6. So your cholesterol should be 222.6 for the probability of type 2 to be point, that is 0.5%, okay? Okay, so let's come to the new concept called as ANOVA. So ANOVA is used for analysis of variance. It's the extension of Z-test. So Z-tests are designed to be used for two groups. ANOVA helps in analysis of variance within and between the groups. Okay. So let's take the concept of one-way ANOVA first. So one-way ANOVA is used to compare two or more than two groups based on one factor. That is, I'm repeating myself once again. One way is comparison of two or more than two groups based on one factor. The example is, let's say a company wants to compare the productivity of 5 employees based on one factor, that is working hours. So this is one way another, because where we are, uh, there are two or more groups, that is there are 5 employees, and based on one factor we are doing comparison, that is we are comparing the productivity based on working hours. Okay, we are based on working hours, we are comparing the productivity of 5 employees. That is the one way ANOVA example. Let's see if we can. Let's see an example for a one-way ANOVA. So here is an example for one-way ANOVA. Okay. So to assess, so before going to one-way ANOVA, let me see. So, okay, there are two. Okay, let me complete the one way to all to two and then way ANOVA as well. So after that, I will move to the ANOVA questions. So in two-way ANOVA, it compares two or more than two groups based on two factors. Let's say a company wants to compare the productivity of 5 employees based on two factors, that is working hours as well as number of tasks completed. So this is more two groups, two or more groups, that is productivity of 5 employees compared is compared based on the factors as well as number of tasks. Here we just took Working hours as one factor. Here we're taking two factors, that is number of tasks also completed. Now let's take into consideration of NV ANOVA. Similarly, like if we had one way, we had one factor consideration, two way, two factor we consider. Based on that, we will get the values. And anyway, comparison of two or more than two groups based on all the factors, that is n factors. Okay. Productivity of employees based on n factors like working hours, number of tasks completed, or leaves taken, and etc. Okay. So before moving, you have to know about F test or F table. F test or F table is used to compare the variance between groups, and this is going to give you answer if our hypothesis, whatever hypothesis we made, is true or not. Okay. If we have to if a null hypothesis is true or not is dependent on F test or F table. That is, we will calculate F, and based on F table we will compare the F calculated and see the F table, and if it is less or greater than F table and F calculated values after comparison, we will say if null hypothesis is true or not. So just understand it is used to compare variance between groups. Okay. F is variance of 1 by variance of 2. It is variance, we know, standard deviation square by 1 by standard deviation 2 square. But according to degrees of freedom, if you go and check the F score table, so if I'm going to show the F table over here. So you see in F table, we have this is V1 and this is V2. Just understand, if variance of A is greater than variance of V, then we will take variance of A to be the numerator and variance of B to be the denominator. If variance of B to be greater than is variance of A, then we will take variance B to be the numerator and variance A to be the denominator. You just understand, if variance of A is equal to variance of B, then we will take any of them as numerator. You have to understand F is always greater than or equal to 1. Okay, it can't be negative. It's always greater than or equal to 1. So now what will happen is that we will take the consideration of V1. Okay, this is V1 distribution. So this is for alpha is equal to 0.05. Okay, so significance of 0.05, we will have the F distribution values over here. Similarly, we have for significance level of 1 and point 1, we have some different values. So it depends on what is the value of significance for F distribution. Okay. So now let's take into consideration the degrees of freedom. Okay. This, you just consider this V1 as the degrees of freedom and V2 as degrees of freedom. But always you have to check what is the value from here. I mean, whatever the highest value is there, that will be V1, and lowest value that will be V2. Okay, highest is V1, lowest is V2. That is how you're going to calculate F1 score. So let's say if your degrees of freedom DF1 is 12 and degrees of freedom DF2 is 2, then the value of the hypothesis is that value, if calculated, is 3.89. Okay, then based on that, we will compare F calculated with that. This is F tabular. Okay, this is F tabular. We will calculate we will calculate F using the data that is given, and that is compared with the F tabular data. So this is all about F score. So let's come to this examples of ANOVA. So let's see ANOVA, one-way ANOVA. To assess the significance of possible variation in performance in a certain test between the convent school of a city, a common test was given to a number of students taken at a random from fifth class of three schools concerned. The result is given as follows. This ABC are the schools. So make the analysis of variance of the given data. Null hypothesis says no significance variation in the schools. Okay. So null hypothesis is no variation between schools. Alternate hypothesis is there is variation between schools. So you have to understand, you have to remember this formula. So source of variation is between the sample, within the sample. So sum of square is sum of square of the columns and sum of square of errors. degrees of freedom is C minus 1 column, number of columns minus 1, and number of data points minus columns within the sample. Mean square is the mean square column and mean square error. Mean square column is SSC, that is sum of square column divided by degree of freedom 1. And this is degree of freedom. Similarly, mean square error is now sum of square error divided by degree of freedom 2. So whatever value is you will get here, this is the F calculated. That is F calculated means some mean square column divided mean square error. So based on the F calculated, we will actually find from F tabular, that is F tabular will be calculated from the degree of freedoms. So whatever degree of freedom you will get here, we'll compare this degree of freedom V1, that is if this is higher, then this is V1 and this is higher, this is V1. So we'll take V1 and V2 from this, that is DF1 from DF2, and we will at the end we will check from the here. So what is the value of V1 and what is the value of V2? And based on that, we will take the F tabular, and after that, okay, after taking the F tabular, we will compare that F tabular with the F calculated value over here. So if F calculated is, let me say once again, if else calculated is greater than F tabular, then it is hypothesis to null hypothesis is false. If F calculated is less than F tabular, that is if F tabular is greater than F calculated, then null hypothesis is true. Okay, that is all about this. Okay, failing to reject hypothesis. So let's see the example now. So we have three schools A, B, C. So now let's take the mean of this A school, that is comes out to be 9 plus 7, 20 plus 30, 30, 33 plus 9, 40 to 50. 50 divided by 5, that is average 10. So mean comes out to be 10 for A, mean comes out to be 11 for B, mean comes out to be 12 for C. Now let's take the overall mean of this. So XA plus XB plus XC divided by 3, that comes out to be 11. So now let's subtract whatever value you have from A, let's subtract that value from the overall mean. So it is 10. So we are subtracting mean of A divided by we are subtracting mean of A by overall mean of ABC. So let's subtract that xa minus x whole bar whole square. So you have to square that also, right? You have to square that. Subtraction is done. Now square it out. So when you square it out, you will get 10 minus 11 minus 1. So square each value. So 10 minus 1 minus 1. So for all 5 points, we have to do that. For all 5, 1, 2, 3, 4, 5, 10 minus 11 minus 1 whole square. Similarly, do for 11 minus 11. And after doing 11 minus 11, then square it out. And then once again 12 minus 11 and square it out for each. So whatever value you get for each, then write that and then do the sum, okay? So for A, the value comes out to be 5 summation. For B, it comes out to be 0. For C, it comes out to be 5. Then sum of square column is sum of square column. Okay, then add all the column values that you get, all the column summations here. You get 5 over here, 0 over here, 5 over. So sum of square column is 10. So substitute value of sum of square column. Now let's calculate the sum of square error. Okay, sum of square error calculation can be done. So whatever mean you get, right here, you get for mean of A bar is mean is 10. So subtract these values by 10. So 9 minus 10 is minus 1, 11 minus 10 is minus 1, 9 minus 10 is minus 1, 11 minus 10 is 1, 13 minus 10 is 3, 9 minus 10 is minus 1, 8 minus 10 is minus 2. Okay, so we have subtracted the values. Now they square it. Okay, 1, 1, 3 square 9, 1, 2 square 4, and it comes out to be the value when you add up, it comes out to be 16. Okay, this comes out to be 16. Similarly, subtract this value by mean of B and square it. You get comes out to be 58. Similarly, subtract these values by mean of C, that comes out to be this value, and then square it. Okay, so then add all this square error. Okay, sum of square error. So when you add this out, you will get 16 plus 58 plus 64. It comes out to be 138. So substitute that value over here. So now what you have to do? Substituting after substituting. So we have degrees of freedom is C minus 1. This is number of columns minus 1. How many columns do we have? 3. So 3 minus 1 is 2. So degree of freedom is 2 here. And within the sample, if we do, Degree of freedom for within the sample is n minus c. N is number of data points. So totally how many data points are, totally how much data, how many data are there? So we have 5 here into 3, 15. So 15 minus number of columns, 3, 12. Okay. So total 15 minus 3, 12. So degree of freedom, 12. Degree of freedom within the sample is 12. So now let's calculate the mean square. Mean square is MSC is SSC by degree of freedom. It comes out to sum of square error is 10 divided by 2. It comes out to be 5. Mean square error is sum of square error divided by degree of freedom. That comes out to be 338 divided by 2 is 7.5. Now we have to take the ratio of mean square of column by mean square error. It comes out to be 0.435. Now we have the, this is F calculated. Understand? This is the F calculated. Now we have to, this is F calculated is 0.435. Now we have to take the F tabular. So we know V1 is 12, that is V1 is this one and V2 is this one. V1 is the degree of freedom with the highest and V2 is the degree of freedom with the lowest. So V1 with 12, V2 is 2. Let's see the value from the tabular data. So V1 is 12, that is this. V2 is 2, that comes out to be 12 and 2, 3.89. Okay. So 3.89 is the value. So if you see F calculated is less than F tabular. So what does it say? F tabular is greater than F calculated. That is null hypothesis is true. Okay. Null hypothesis is true. That is no variation between school A, B, and C. That was the assumption, right? No variation between schools. That is the assumption is true. So there is two-way ANOVA. The following data represents the number of units of tablet production per day by 5 different technicians by using 4 different machines. So these are the 4 different machines and these are the 5 different technicians. So for solving two-way ANOVA, you have to apply this formula and between source of variance should be between the columns and between the rows, and then you have to take the residual squares and then you have to do the total sum of square. Okay, so sum of square is sum of square along row, sum of square error, and sum of square total. So we have degrees of freedom for row, column is C minus 1, row is C and R minus 1. For residual error, you have to multiply C minus 1 by R minus 1, and the total number of square is degree of freedom is N minus 1. For this, it is number of data points minus 1. The mean square error, mean sum of square is SSC divided by C minus 1. For rows is SSR divided by R minus 1. For residual error is SSE divided by C minus 1 by R minus 1. And if you want the between the columns, if you want the score, then MSC divided by SS, MSC. Then if you want between the rows, MSR divided by MSE. So calculation of grand total and correction factor. So we have to take the mid value. So whatever mid value is there from here, so we have to take. So we have to take it by taking the lowest and highest average. So lowest here is 42, and highest here is 62. So 42 plus 62 is divided by 2 gives the mid value. Let's, for convenience, let's take 50. For calculation, it will be easy. Let's take 50. So now what you have to do, whatever value you got, subtract each data point value, subtract each value by 50. And whatever value you got from that, add up to row column, add up to column columns. Like you got 54 minus 50, 48 minus 50, 57 minus 50, and 46 minus 50. So add whatever value at the end you got. 4 plus minus 2, 2, 2 plus 7, 5, 5 plus minus 4, 4 plus minus 4 minus 2 is 2, 2 plus 7, 9 minus 4 is 5. So add row total, add column total like that. After subtracting each value, add column total and row total, and take the grand total of row total and column total, which comes out to be 20. Okay. So now we have to find correction factor. Correction factor is the grand total whole square divided by number of data points, that is number of values. So we have a total is, there are 5 into 4. There are technicians 5, 4 machines, 5 into 4, 20. So divided by 20. N is total observations, it's 20. So 20 square divided by 20 comes out to be 20. So now let's calculate SSC. So for the calculation of SSC, you have to take summation of A square by NA. NA is the total number of points, like total technicians. technicians, number of technicians, that is 3 to 5 technicians are there. That is column wise. Okay, SSE is for sum of square columns. So for column we have 5, total of 5 of the technicians. Summation of A whole square, summation of A whole square if you want to do. So let's see what is the summation of A whole square. So this is the column, right? Column data. So we have to take this column data 5 square plus 6 minus square whole minus 6 square plus 38 whole square by minus 7 whole square divided by 5 minus 20 whole square divided by 20. That is the correction factor. Okay. So these values divided by the total technicians 5 number of and minus correction factor, the value comes out to be 288.8. So sum of square column. Similarly, sum of square rows you have to do. You have to take square these values 5 square, 21 square, 14 square, 1 square, 7 square divided by number of machines, that is 4, right? So number of machines is 4, that is row wise. Okay. Totally there are 4 values. So instead of taking machines and this thing, you just take 1, 2, yeah, we have to take that only. So now let's take the number of machines row wise. So let's 4. So if you do that calculation and minus grand total, that is t square by n. Correction factor, if you do, you will get sum of square rows, yes, 158. Now let's calculate sum of square total. Okay, sum of square total square is the whatever value you get here, right? Whatever value you have, 4, 6, 6, 3, minus 2, 0, 4, 4. Square all the values and sum it up. From here till here, minus 2. Okay. So whatever value you have, 4 square, 6 square, so let's 6 square, 3 square, minus 2 square. You add it all and square it all and add it up. All the data, that is 20 values are there for sum of square total. So sum of square of all observation. So there are 20 observation. You will get each value, square it, and then minus by correction factor. You get sum of square total to be 564. Now substitute all the values here. Sum of square column is 288.8. Sum of square rows is 158. Sum of square total is 564. So sorry, residual error is sum of square total minus this plus this. Okay, sum of square total is 564 minus of bracket 288.8 plus 158, which comes out to be 117.2. This is our residual error. So now for degrees of freedom for column, it's total number of columns divided by minus 1 is 3 column. The degree of freedom is 3 for this between the columns, and between the rows we will have total number of rows 5 minus 1 4 degrees of freedom. And for residual errors we will have multiplication of degrees of freedom columns and degrees of freedom rows, that is 12. Okay, 4 5 4 into 3 12. Now we have to find the total sum of square degrees of freedom, which is total 20 observation and we minus 1, that is 19. Now let's calculate mean column, mean square sum of square. So mean sum of square is this divided by degrees of freedom, and similarly between the rows divided by degrees of freedom, and sum of square total divided by their respective degree of freedom. So we'll get 96.27, 39.5, and 7.7. So for between the columns, the f value for between the columns is mean square column divided by mean square residual error. Okay, so which comes out to be 9.86, and similarly mean square rows divided by mean square residual error, that comes out to be 4.05. So from the tabular data, check between the columns what is the value residual error. Okay, so degree of freedom 12 is given and degree of freedom 2 is 3. 12 3. What is the value for 12 3? So we have 12 as this value and 3. It comes out to be 3.49. Okay, so F tabular is 3.49. So what do we get? F tabular is 3.49. Okay, this is the value. So when you see that F tabular is less than F calculated. So what does it say? Null hypothesis is rejected. There is significant variation between the columns. Okay. Now let's see between this and between the rows if there is any significant change. So 12 and 2, right? 12 and 4. So 12 and 4. If we see 12, df v1 is 12 and v2 is 4, it comes out to be 3.26. 3.26 is here. And if you see tabular is once again less than F calculated because tabular is 3.26 and calculated is 4.05. So in first case, 9.86 is greater than the 3.49 because of that where rejection region null hypothesis is rejected. And once again is 4.05 greater than 3.26 since F tabular F calculated. F tabular lies within rejection region. So it null hypothesis is rejected. So there is significant variation between the rules. So this is all about the hypothesis testing and hope you enjoyed the session. Thank you for attending the session. I will become covering all the other related statistics and the statistics for data science that is required in the next classes. Thank you.